The only difference with the hyperbola to the ellipse is that the eccentricity is bigger than 1. So that multiple is bigger than 1. So therefore, let's get it right, the distance to the focus will be greater than the distance to the directrix in a hyperbola, because we're saying the eccentricity is greater than 1. I think that works out. Have I said it the right way around? Anyway, let's see. Hyperbola. As far as the actual equation of the hyperbola, the difference is now the negative sign in there. So if you see you've got x squared, y squared, you're thinking circle. Oh, coefficients aren't the same, can't be a circle. If the sign is the same, we're talking ellipse. If the sign is different, we're talking hyperbola. Slight difference, you'll see it's e squared minus 1 instead of 1 minus e squared. Has to be, because the eccentricity is greater than 1. So if I went 1 minus e squared, I'd get a negative number. How can b squared be negative? It can't be. So that's the main difference between the ellipse and the hyperbola. The ellipse will have 1 minus e squared, whereas the hyperbola will have e squared minus 1. It means for the eccentricity equation, when we rearrange it, instead of having a squared minus b squared, we'll have a squared plus b squared on the top there. Okay, the lovely thing is, and I'm not going to rederive it like I did the last one, but the foci turn out to be exactly the same. It's still a times e. It's still that. And the directrices are still a divided by e, but you'll notice the placement of the directrices are now different. Right? The ellipse, the directrices were on the outside, whereas with the hyperbola, the directrices are on the inside. We have something with the hyperbola that we don't have with the other shapes, and they are, of course, asymptotes. And the asymptotes of a hyperbola, again, that ratio of b over a, remember that auxiliary circle method? I said the ratio of b over a when we were plotting where to go. That becomes important here as well, because that becomes the equation of the asymptotes. B over a x. And just drawing the hyperbola. So it's not how we're used to seeing a hyperbola. We're used to seeing a hyperbola where the coordinate axes are those asymptotes. So we're like have rotated the hyperbola. And we'll see more about that later when we look at what we call the rectangular hyperbola. Now, if you see the x squared being negative, so it's got nothing to do with which one's bigger, the b squared or the a squared. With the ellipse, it was the size of b squared and a squared which determined where the foci are. With the hyperbola, it's the negative sign. Right? The positive tells you where the foci is. So if you see y squared on b squared minus x squared on a squared, that's telling me that the foci is on the y-axis, not the x-axis. Okay. And so we swap everything around again like we did with the other one. So a squared will equal b squared e squared minus 1 instead of b squared equaling a squared. So the b's and a's swap around again. Foci will be plus or minus be. Directrices b divided by e, so the same sort of thing. Interestingly, the asymptote doesn't change. It's still b on a. Still b on a. Well, let's do a basic one. X squared on 9 minus y squared on 16. It is our standard one. Eccentricity. Well, a squared is 9. A is 3. Eccentricity then, a squared plus b squared on a squared. I get 5/3 for the eccentricity. So I've got that. Foci, a times e. We get 5. Directrices, a divided by e. 9 divided by 5. And the asymptotes, b over a, so 4 over 3, plus or minus 4/3 x. There we go.